Happy Friday, everyone. We're almost at the end of the first week. It's amazing. Today we're going to finish up all these math examples. Before we get into those, I just wanted to clarify some detail from the last lecture because a couple students approached me because they were confused about it. And that is the fact that where'd it go? Okay. It's about inequalities. Not sure if how much I should generalize this. I'm going to use a specific number so you don't get bogged down in the letters too much. We were working with statements like x less than 5 implies that x is less than or equal to 5. So if you're confused by this, hopefully you remember seeing something like this. Just going to explain this again, that x being less than or equal to 5 is the same thing as saying x is less than 5, or x is equal to 5. This is an or statement, so only one of those statements within it has to be true for the whole thing to be true. We found in a previous example, x being less than 5. Yeah?
Wait, so x is less than 5? You could say x is less than infinity?
Yeah. Like,
Like, you know when you have less than or equal to?
mm-hmm.
That number could just be bigger than 5 and just be okay.
Oh yeah, like 5, the number 5 isn't super important to that example. I just wanted to use a specific number to make it a bit clear. And there's actually a point that I think is similar that I was going to get to. So we have that x is less than 5, and thus this entire thing is true. And to give another example of how that or statement works, I could replace x being equal to 5 with whatever I want. Oh, I hope this doesn't keep happening. So we know that x being less than 5 is true. Because of how or statements work, we know that that's true, so at least one of these two statements is true. The other statement can be whatever bullshit we want. 0 equals 1? Who cares? That's obviously false, but to make an or statement true, only at least one of its parts has to be true. And in case you aren't convinced yet, one other thing you could do, and this is a good general bit of advice that applies to any logical statement that you don't get, you can make a truth table. So you could imagine p being something true, like our x that's less than 5 from that old example. Q being whatever you want, x equals 5, 0 equals 1, whatever. And you see that if p is true, then p or q is true, regardless of what q is. This also works for q. If q is true, then p or q is true, regardless of what p is. So the main lesson here is that if you have a strict inequality like x is less than 5, you could use that to say that, I don't know what the term for this is, less strict inequality? You could say that x being less than or equal to 5 is true. The more general, probably more valuable lesson is that if there's a step in a proof that you don't get, or more likely some logical rule found in the lectures that you don't get, make a truth table and it might help you understand it. Now back to the examples. I think I might have gone a bit too slow last time because we have a lot to go through. Because of that, I hope this doesn't keep happening. Come on, get a screen to think of display things, whatever. If the screen goes out for more than like 10 seconds and I'm just yapping, let me know and I'll jiggle the cables a bit. Anyway, what was I saying? That we have a lot to go through. I'm going to skip forward quite a few slides onto what I think are the most important examples. I'm going to go through those, and if we have time at the end of class, I'll go back to the less important but potentially foundational examples. So we're going to go way ahead, I think to slide 27. Because I want to talk about quantifiers. These are going to be super important. Statements like these might look like a bunch of mathematical mumbo-jumbo, and that's for good reason. They are mathematical mumbo-jumbo, but these are actually of a very similar form to statements that you'll have to prove in order to show that certain algorithms have certain important properties. We'll get to that eventually. This statement is saying that for all m in the natural numbers, there exists an n in the natural numbers such that this inequality is true. The order of the quantifiers is super important. Since we have for all m, that means we can't make any assumptions about m. Our proof has to work for any given natural number. But since we say for all m there exists an n, we can define n in terms of m because I think an easier example is that for all n in integers, ooh, that's terrible. There exists m in the integers such that n plus m equals 0. That is a fact that you'll know it's additive inverses. You have a number, there exists a number that is just its negation. Negative numbers exist. This is going a bit off track with the example, but I just wanted to show a simpler one first. If you wanted to prove that, you would say something along the lines of m equals negative n. Someone gives you an integer n, you know nothing about it, you can't assume anything about it, but since for all n there is an m can be different depending on what n is. In this case, m is the additive inverse of n. So with that out of the way, let's go back to the inequality that we're actually wanting to show. And what are we going to do next? Right, this is an important sort of starter example of how the actual proof that you hand in for an assignment that you make in the real world if you do research will kind of be backwards from your rough work. When you're trying to figure out how to prove this, your first step is not going to be, oh, maybe n should be m plus 2. Uh-huh. The steps that you take at first will sort of be in reverse from the proof that you produce. So let's say we're working on an assignment, not together, that would be academic dishonesty. And we want to make that inequality true. And since we're starting with for all m, there exists an n, we can't do anything to m, but our goal is to restate n in terms of m. In this case, we can make it quite simple, actually. All of these terms have n in them, so we could simplify the whole thing by just dividing both sides of the equation by n. That's a lot better. Now we only have one term with n. And we're much closer to our goal of defining n in terms of m. Let's just add 1 to both sides. And there. From this algebra, we see that if n is greater than m plus 1, then the inequality we want to prove is true. So we have to choose a specific n for our m. I don't know, what's the smallest integer you could think of that's greater than m plus 1? Well, its successor, m plus 2. Any value greater than m plus 1 would work. You could say n equals m plus 3 billion, but we'll keep things simple and define it as m plus 2. And look at that. The last thing we did in our rough work is the first step of the actual proof. I'm not going to bother rewriting this in LaTeX to save time. I'll just go through the final proofs that are actually on the slides. So m plus 2 is greater than m plus 1. So we have this inequality, which just happens to be the last step in our rough work. We multiply the inequality by n to get this inequality, just like how we divided it by n in the middle step of our rough work. And then, since m was arbitrary, we see that we've proven the thing we wanted to show, which was what we started with in the rough work. Yippee! This is going to show up a lot, and it's going to get a bit more complicated from here. There are going to be a lot of examples where the proofwriter just chooses some value for a variable that seems to come out of nowhere, but it didn't come out of nowhere. It came from experimenting with the result of the proof and finding something that would fit into it. Are there any notes that I haven't gone through yet? Oh yeah, it's worth noting that not everyone agrees on what the first natural number is. The convention we're going to use in this course is that the first natural number is 1. I like that because natural numbers are the ones you learned first. Start counting at 1, not 0. In other disciplines, including certain parts of computer science, in fact, the first natural number is 0. But this part of the course is more pure math, so we're going to start with 1. You could think about this on your own time. We don't have time for this. And this bit is sort of a summary of what I've been talking about. You take the inequality that's in the thing you want to prove, and then you can't use it for anything in your final proof because you haven't proved it yet. But in your rough work, you can assume it and then try and find out what values of the variables fit into it. Okay, this is getting good now. Oh, and the previous slide also says something that's important here. Quantifiers are addressed in order, left to right. So previously, we had for all m, there exists n. That meant m was totally arbitrary, couldn't assume anything about it. And then we defined n in terms of m. Now we have there exists an m such that for all n, this implication is true. This means that we can choose our value for m, but then we can't do anything about n, just because of the order of the quantifiers. If your proof included some arbitrary m, and then you defined n in terms of m, you lose marks, possibly all of them, because that would be wrong. So let's look at the proof. Let m equal 20. Sure? Where did they come up with that? Well, this is because we're sort of working backwards again. Although you could probably see, or begin to see how they got the number 20 because 20 appears in the thing we want to prove. Oh, and note that in this case, I guess we can assume something about n, and that's that it is greater than m. And actually, just to illustrate this example a bit more, I'm going to quickly graph these two sides of the inequality. So you could say this is n plus 20, and that's n squared. We're showing the fact that eventually there's a point at which, or after which, n squared is always greater than n plus 20. So anyway, how are we going to do that? We're going to see our first instance of a trick that'll be used in proofs throughout the course. I think a later slide calls it the rounding up trick. So we want to simplify one side of the equation to make it easier to compare with the other side. Right now, on one side of the inequality, not an equation, sorry, we have a variable and a constant, which is pretty clunky. We can't easily compare it to the other side, which is just a variable. We can't divide everything by n without introducing a 20 over n term. Ideally, we want to do something like step 3 of the proof that changes that n plus 20 side of the term, or side of the inequality, into something with only one term. Now, is there anything else I have to do before just saying, oh, maybe it's greater than 20? Yeah, I think the original writer of this proof did indeed guess that maybe n is at least 20, because if you tried this out, so now we have a new inequality under our tentative assumption that n is greater than 20, which might be wrong. You'll probably guess, check, and correct a couple different possible bounds for your variables in the process of doing rough work. So we know for sure that n plus 20 is definitely less than n squared, and that n plus 20 is less than 2n. But we don't know the relationship between 2n and n squared. If we can show that 2n is less than n squared, let me just write that down. If we show that 2n is less than n squared, then we'll get the inequality chain, you could call it. We get the thing we want to prove. And now we just have our lonely 2n. We want to eventually show that it's less than n squared. And to do that, we can use the properties of n that we previously thought about, that being that n is greater than 20. So if n is greater than 20, it's also greater than 2, because, as you know, 2 is less than 20. Because of that, or since n is greater than 2, we could make a new inequality that just replaces 2 with another n. And we have our n squared. Success. This stuff is a bit weird. Manipulating inequalities is a bit of an art form. Don't worry if you don't get this example. you will do so many of these that this will look easy eventually. Yes? Sorry, what did you say? Okay. Was it this thing? Just a moment. I could upload these annotated slides to you and learn as well, if that would be helpful. Cool, I'll do that. And I think you put your hand up second.
Yeah. What's the first part? So there's one M, or like, there is one M in the natural number, and all of the N have to follow it on the right?
Yeah, I kind of glossed past this part, and there are slides earlier in this lecture that I skipped for time constraints talking about proving an if-then statement. But the essence of this is that usually if we have a for all statement, we wouldn't be able to assume anything about n. But in this case, we're proving that if n is greater than m, then n plus 20 is less than n squared. And that lets us assume that n is greater than m, because proving an if-then statement always involves assuming the if.
So M is 2 and N is 3, that's still true?
M is 2 and n is 3. Then the statement just, wait. Okay, I think then the statement would be false for that specific value of m.
Then it's not true at all.
But then it would be false if the quantifier were for all. What? This app's okay, I guess. Yeah, so if it were for all m, then indeed you would have just found a counterexample.
Oh, so
But-
it's just an element, so we just find one.
Yeah, like this is true for m equals 20. It's true for m equals 1,000,000. It's not true for m equals 1, but that's okay because we only had to find one value of m. Okay, what was your question?
So, like, instead of writing it like this, if we have written like, let m be 20, and then after that we said that 20 is greater than 2, and then you multiply n on both sides, and then you get n squared is greater than 2n. So essentially, like, whatever is written there, we just kind of do the opposite, but then it'd still be right.
Oh, okay. Sorry, I'm just thinking about whether I have time to look into that, because I would want to write that down myself so I could actually look at it before I verify it. Yeah, let's try it. Can you go through your steps again?
Yeah, so I start with let n be 20, which means that n is greater than 40. Now, 20 is greater than 2, so that implies n is greater than 2. Now, multiply n on both sides.
Both sides of n greater than 20?
No, n greater than 2.
Okay. So, like, that? Pardon me?
Yeah.
Okay. And then you're asking, would you be able to use that to show the inequality?
Yeah. So
Uh,
instead of step 3 that's in the slide, like that would be my step 3.
Yeah. Yeah, I think this is good. You would just have to do a little bit more that you probably already had in mind. So this last step is true because n is greater than 20. And yeah, you have the inequality that we wanted, so that would totally work. Yeah?
I
quick question. What was the process of letting m equals 20? Was rounding?
Yeah.
What was an m?
That was, you could kind of chalk it up to a lucky guess. The goal here was to make it so this side of the inequality, which has two terms, we want to change that to only have one term so that it's more easily comparable to the other side. And one way to do that is to make it so all of the terms are multiplied by the same variable. And from there we got, oh, maybe if n is at least 20, then we can replace the 20 with an n, and then eventually turn n plus 20 into something that's just one term with n.
So you round up n plus 20 to get to n.
Exactly.
So that you can compare it to n squared.
Exactly, yeah. Yeah?
Since we did graph it and we do have n greater than n, could we not just chalk up n to like the intersection point at which n squared is greater than n plus 20 and then do that?
Yeah, totally. Your final proof should still look a bit like this, but yeah, graphing and then using geometric qualities of the functions you're working with is a really good strategy for rough work. Yeah.
We don't have to show you at all how we got n equals 20.
Nope. If it works and you prove that it works, it works. Excellent questions, everyone. Now, what's next? First note is the thing about the quantifiers. Our first quantifier was there exists an m, and thus our first step was of the final proof was to propose a value for m. And m equals 20 is the simplest value that we could find from this rough work. But you could do a lot of other different values. M equals 1,000,000 would work. And a bit more notation. All these quantifiers followed by the assumptions that we're making can get a bit clunky. We can shorten this a bit. Have something like, for all n in the natural numbers, then n greater than m implies whatever. We could just say, for all n that are greater than m. Be very, very careful about not specifying the set that this is in. This statement would be valid if we had some sort of convention for assuming that all variables are natural numbers unless otherwise stated. But I'm pretty sure at some point in these slides we say that the convention is that all variables are real numbers unless otherwise stated. So just make sure the reader understands the parts you're leaving out, and you can shorten it a bit. Ah, sick, rounding up. Yeah, this I probably won't go over because I've already talked about it at length a bit. But this will be a good reference if you want to refresh yourself on what I'm saying. We want to simplify the complicated side so that it's easier to compare with the other one. And then also, we want to make the smaller side bigger because that's what made our sort of chain of inequalities work. If we changed n plus 20 into something less than that, let's say just n, and then showed that n is less than n squared, that wouldn't really show us anything because it doesn't follow from that. I'm just going to write this here for illustration. N being less than n squared doesn't imply that n plus 20 is less than n squared, but 2n being less than n squared does imply that n plus 20 is less than n squared. So when you simplify your like complicated side, it needs to come closer to the other side of the inequality so that we can make, an inequality chain like this true. Oh yeah, all variables are assumed to be real numbers. So that that example of this simplification isn't actually that good. It should probably be the integers. So what do we have now? Well, first off, we have that, oh wait, not integers. It should be the reals. There we go. We have that simplification in action. Instead of there exists an m in the real numbers such that there exists an n in the real numbers, if m is greater than 0 and n is greater than m, then 8n squared plus 5 is less than n cubed. That was exhausting. Instead of that, we could just say there exists an m greater than 0 such that for all n greater than m, 8n squared plus 5 is less than n cubed. For this one, we're going to use a similar trick. It's just going to be a bit more complicated. We have this inequality that we want to be true, and we just need to find a value of m such that a value of m such that for all n greater than that m, the inequality holds. This is, in principle, a similar sort of graphing-esque problem. Trust me, it happens eventually. So like before, we want to find a value after which 8n squared plus 5 is always less than n cubed. How are we going to do that? Well, maybe we can say that n. Wait, how am I going to organize this? I think I'm going to move this a bit to the side. And then write down guesses that we're making at the value on the other side. So maybe n is greater than 5, similar to that n greater than 20 approach from last time. Then we could say 8n squared plus 5 is less than 8n squared plus n. Well, maybe you can divide all the terms by n and you get something like 8n plus 1 is less than n cubed, but then you're in the exact same situation. We would have a constant term that's ugly to work with. Maybe n is greater than root 5. I know that that is an implication of that other guess we made, but it lets you manipulate the inequality in a different way, I guess. The reason I guessed root 5 is because guessing a value to change 5 into n didn't do anything. So maybe we want to change 5 into n squared. Okay, now we're getting somewhere. At this point, if we show that 9n squared is less than n cubed, we'll find that the original inequality is true for the same number line related reasons as earlier. So let's try dividing both sides by n squared. Wow, we have n greater than 9. Luckily, this doesn't contradict our earlier guess of n greater than square root of 5. In future proofs, you might end up with n being greater than multiple different expressions that have different variables, and we'll find a way to work around that later. But for now, we just have that n is greater than 2 different constants, so we could just say that n is greater than the greater of those 2 constants. And that's how we derive that, in this case, n is greater than 9. Remember, we want n is greater than m, so we start our formal proof with m equals 9. And the rest is sort of our rough work in reverse. We have m equals 9, which we just figured out by playing around with the inequality that we want to prove. And now we're proving that it fits in. Okay, last example, 5 minutes left. Not sure what to do here. I think I will squeeze as much of an explanation of the example into the last 5 minutes. Or did you have a question? Oh, okay, bring it.
So, we just dividing random numbers until it works?
Exactly.
Really?
Yeah. Well, choosing, pardon me? Yeah, I was going to say choosing purely random numbers is probably a bad strategy. No guarantees that you'll finish your homework before the heat death of the universe. The truth is, it's a bit smarter than choosing random values. Through practice, and lots of it, you'll get good at manipulating the inequalities that you're given to find values that probably work, and then checking your work and making sure that it makes the inequality true. So it's not random guessing, it's educated guessing. So what can I say about this one in 5 minutes, 4 minutes? Well, I'll show that this is a good example of a chosen value that really makes you go, how the hell did they think of this? But the principle behind the rough work is the same as last time. We started with the small side, and we want to make it more easily comparable with the big side, as well as bigger so that the chain of inequalities works. In the rough work, we would say, oh, we have 2 to the n and 3 to the n. 2 to the n is less than 3 to the n, so I could use that fact to make it larger and just have 2 terms of 3 to the n. And then if I show that this inequality holds, the original inequality will hold. Then they just rearrange the terms of it to get all the exponential n's on the same side. Divide both sides by 3 to the n, and also divide both sides by m. And then the power, or the rules to do with exponents that you learned in high school apply. 4 to the n divided by 3 to the n is equal to 4 divided by 3, and that whole thing to the power of n. Use logarithms to sort of drag the n out of its position as an exponent. In this case, you take the log base 4/3 of both sides to get n greater than log 4/3 of 2 to the m. And then since, since n had to be greater than that log expression, we just set it equal to that plus 1, because that's a successor. That's all for this week. Next week, we're going to keep talking about math, but it's slowly going to approach actual comp sci coding related stuff. Have a great weekend, everyone.